All right, so let's continue talking about combustion reaction, energy change because of combustion and so forth. And this is the table that you'll be coming back to again and again, one of the tables. There are other sources of this. You can also find this on the internet, by the way. So this is the energy content of these different molecules we're talking about. So in the last couple of videos, I wrote a bunch of equations, balanced equations, added up the energy content and gotten numbers that says energy released per mole and so forth. You might wonder, I said, can I just write any reaction and can I just add up any enthalpy content per molecule and so forth? The answer is, of course, not. You can't. Just because you can write a balanced reaction doesn't mean that it will actually occur in that way in nature, right? So the important thing to remember is that the species that you're writing in equation form must exist, and the reaction is going to be feasible and practical. So you just can't write any reaction and therefore say, hey, I'm going to get some energy release from this reaction. So, so let's go back to the methane case. This is the oxidation of methane, and we get the energy release per mole of methane, right? So the question is, if I were to reverse that reaction, carbon dioxide plus 2H2O giving you CH4 and 2O2, that's a balanced reaction, right? So can you make methane from carbon dioxide and water like that? It appears as if this, you should be able to, right? The equation is balanced and so forth. Well, it's not that trivial. I mean, certainly methane is formed somehow, right, from these carbon compounds. But just because you can write a reaction doesn't mean that it's actually going to happen. So keep that in mind, right? So in this particular case, it looks like if you put energy into carbon dioxide and water, maybe there is a way to actually make methane. Yeah, perhaps, but let's not get into that specifics except to say that there are ways in which you can make something by putting energy into a reaction as opposed to extracting energy from a reaction. Okay, keep that in mind. So yeah, perhaps there is a way to make methane from this type of reaction under some conditions. Extraordinarily difficult. It's not that easy. Then the other question is, well, why not water? Can I write a chemical reaction with water and oxygen and expect it to be used as a fuel? I mean, you can imagine water can be just hydrogen and oxygen, right? And you may have heard about fuel cell. What you actually is you take combine hydrogen and oxygen to form water and create energy along the way. So you can imagine that here you need energy to split it into hydrogen and water. Here you get energy when you combine the two, right? So opposite. This one generates energy. This one will require energy in order to happen, right? So stepping back, so just because you can write a chemical reaction of some kind doesn't mean that it's feasible. Keep that in mind. And as a reminder, in calculations in the last few videos, you saw that methane gives us the highest amount of energy release per mole of carbon, right? So the question is, as I mentioned, so why not just use methane? Why are we using inefficient fuels like gasoline and so forth, right? A very, very important thing to remember is that even though the energy per mole of carbon is the highest for methane, as the carbon number increases, the total amount of energy that is generated also goes up. So while the per mole energy release for methane is the highest, it's difficult to carry that much methane gas, for example, in a car, right? To have the appropriate amount of energy to go, say, long distances. So one possible solution to that is don't use methane gas, liquefy it, so the volume will go down, so you can carry more of it. So that's one possibility. That could be more efficient. In fact, one of the things we've actually seen recently because of the shale revolution, the fracking revolution, is that the United States is making so much gas. So for example, we are now watching the automobiles, trucks, and so forth retrofitted to use compressed natural gas, so liquefied natural gas as a source of the fuel. It's in terms of the miles per gallon equivalent of gasoline is actually gotten to be cheaper. So the one reason we're going back to using natural gas in automobiles and trucks and so forth, it's not very big right now, but it's growing, is because the price of natural gas has come down so that even if we add the cost of liquefying the gas and then transporting it and then putting it into automobiles, it still turns out to be cheaper than using gasoline. So you can use natural gas now, which because of the shale revolution, which has made the prices really competitive with gasoline. So, and then a couple of quick slides as a reminder of how the gasoline engine works. If you click on the PDF, it'll take you to this website, how gasoline engine works, and how diesel engine works. If you remember, the diesel engine doesn't have spark plugs, and it uses the fuel is self-igniting under high pressure and temperature. And just a quick reminder about the compositions. Natural gas is typically 1 to 2, mostly 1 carbon, and as the carbon increases, the molecular weight also increases. And these are all different fuels. Typically, this gasoline we understand. Kerosene, or say, it's 12 to 15 is where aviation fuel actually is actually found and used, and it got higher molecular weights. It's diesel. As the carbon increases to 18, 20, and 22, for example, we get essentially becomes oil. So it becomes lubricating oil and so forth. So this is just a reminder of as carbon number increases, composition therefore changes. Their use as fuel therefore also changes.